All right. So let me get started with today's session. So a very good morning and welcome you all. We have with us Mayank Vatsa, who is a professor at IIT Jodhpur, I think in computer science, right? But I don't have his formal bio- biography, therefore I'm just saying whatever I know about Mayank because I have known him very closely when he was a professor in Triple IT, and he is one of these early professors in Triple IT, and now he is in IIT Jodhpur. He's doing some incredible things, but a few things worth mention here is that he is a Swarna Jayanti fellow in engineering, which is a great achievement by itself because it's not very easy to sort of get such an important fellowship in engineering because engineering is a very broad sort of a area. And he also served as the vice president of IEEE Biometric Council because a lot of his works are focused on biometrics. I think mostly focused on biometrics, and he applies deep learning and machine learning, all these things there. And he started IEEE transaction on biometrics, behavior, and identity science. So it's kind of a very core area of research. And there was no IEEE transaction before, and the credit goes to him to start that journal, which has now become extremely prominent. And I think Mayank, I'm not sure if it has already got the impact factor or it will soon get the first impact factor. But anyway, Mayank
Yeah,
will talk more about that. But also, I think he has done enormous amount of science. Keeping the quality of the science aside, I think he has an enormous amount of science. I think it is like 350 plus publications, 10,000 citations. At his age, he's not very old, by the way. So he's just like, you know, just over 40, and that's incredible. I think this a huge success, I'd say. And he serves also as an adjunct faculty at West Virginia University, US, right? And he has been doing so for some time now, as far as I know, and also an adjunct faculty at Triple IT Delhi. A lot of things that we enjoy today in Triple IT in terms of artificial intelligence, the Center for Artificial Intelligence, funded by Infosys and all that. So he's one of the key man, right? I mean, behind making all these things. And he started the CS plus AI program in Triple IT, which is a very attractive one for students these days. And he's doing too many things. I think in IIT Jodhpur, I'd request uh, Mayank to sort of give a brief overview of what all he's doing there as well. Because I didn't have a formal biography, so I just said impromptu whatever I knew about Mayank. Over to you, Mayank.
thank you, Dibarka. Thanks for the nice introduction. Means you have pretty much summarized majority of the things. Uh, was here at IIT Jodhpur. I'm also heading the Technology and Innovation Hub on CVAR. We call it as I have Drishti. And very recently, I was also made professor in charge for corporate relations. This is a new office we are setting up over here for engaging more with corporates, a separate dean's office essentially. Uh, so these are some of the things. More importantly, we are working in. I'm actually so I have a lab which has more than 14, 15 PhD students working with some exciting research areas, including now the uh, healthcare domain. While biometrics has been my bread and butter for so many years, it still is actually my bread and butter, but slowly we are also looking into the problems of medical image classification. Uh, Over the last few years, slowly we were picking up, but now we have three PhD students right now working on this kind of problems, particularly related to the title of today's talk is on small sample size, trustworthy medical classification problems. This is what actually I've thought that means the best of uh, this particular group of population. I think this could be an interesting topic, and this is what I mentioned Professor Raghava when he invited me that I would like to talk about this problem statement because we are very passionate about this problem statement, and I hope now my screen is in a full screen mode. So here, if you see, there are two keywords in this particular title: small sample size problems and trustworthy AI. So let me first go through these two things individually to motivate and then explain like the problem statement or what we are interested in. Okay, and then we'll talk about a couple of approaches that we have worked upon, including one of our recent paper for COVID extra analysis. So let's first understand what do we mean by small sample size problems. So if you look at the growth in the AI domain, including in autonomous cars, when people are sleeping in the car, like this is a Tesla car running and the person whose driver is sleeping, a huge growth has happened in the last few years. Conferences like CVPR, NeurIPS, ICLR, they are seeing surge of papers. I know in CVPR 2022, next year, uh, the PC chairs are working on somewhere around 9,000 to 10,000 submissions. Just one conference alone, right? And then they would accept about 25% papers. NeurIPS recently had almost 8,000 submissions. So not many research threads are going on and a lot of progress is happening. And this whole buzz that is going around, we can very safely say this is because of the way we have progressed in the deep learning world. Right, so it's a data-driven technology, and it has seen a lot of good results. I would say exemplary results in object recognition, face recognition, even in autonomous driving combined with other technologies. This has actually done wonders, and it is very safely we can say that given a sufficiently large data set for a particular problem, there is a deep learning architecture that would give the state of art performance. This is a very safe statement these days. Once you have sufficient data, like millions of data points, you can safely just put this into a deep learning architecture. Deep learning architecture will give you some good results, and there will be one deep learning architecture which will beat everyone else. And next year there will be another deep learning architecture which will beat the previous one, and so on and so forth. So uh, very exciting work is going on. But the key question actually comes in how large is large. Means given the huge amount of training data that one can actually generate for many problems, there will be a deep learning architecture sitting somewhere which can actually provide astonishing results. So this is a chart which shows that generally in 70s, 80s, even in 90s, or even when I was doing my PhD, the largest training data that we had was a couple of thousand only. Today, when we are talking about training deep learning models, we always talk about how many million samples you have. Right? So earlier, the entire data set for training, testing, everything was few hundred thousand samples. When few hundred thousand was considered a very large data set. So what has moved on from large to very large to extra large or whatnot in the future. So more the data that you have, better the performance you can expect from the deep learning architectures these days. Right. But the important part here is that particularly in the healthcare and medical domain, we always try to look at that there are several problems which are for which we cannot collect the data. Right? So the focus in the healthcare domain in many diseases and many applications is on the data sets which are very small. And then I'll show you some of the examples in the next slide. But just think this way: uh, for when the COVID came in, how many samples the researchers had to begin with building screening models or diagnostic models? Though we had like thousands and thousands of cases coming in, but the samples for training the model were very few, and particularly the ground truth models were very few. So researchers had a hard time even actually starting to begin with, like particularly the AI researchers, that how do we actually start in building models when we have very few training samples. with ground truth information. Think of a rare disease problem. When the entire world or in the entire region, if you have only 500 samples, how do you ensure that you build AI models for such rare diseases? Like the example of iris melanoma, you have to find patients associated to iris melanoma to collect the data and then use it for training the algorithm. If your entire population set for building the training data set is very small, let's say a few hundred, 500 samples, how do you actually train a deep learning architecture and use the power of deep learning for these kinds of applications? Right? So I'll show you in some next few slides that even for facial analysis for newborns, like for adult faces, we can say how happy we are, angry we are, and so on and so forth. But with respect to newborn facial analysis for healthcare applications, we don't have data sets. In fact, the only data set which is available, uh, which has newborn faces, uh, has barely like 2,000 samples. Now, how do you train algorithms for these kinds of applications? That is a big research question. So deep learning for small sample size problems is going to be a research challenge. And when we make statements, we can very safely make statements that this is something exciting, means that this is at least my lab is working on. And then here means you see on the right hand side, lower panel, two examples when, and these are classical examples when the deep learning architectures were actually failing miserably. We all know like Google image search, right? So if you give a image to Google image search, it will classify into one of the classes. So when we give, let's say, a flood image to Google image search, originally it classified as a toilet image. And this was when last year in Bihar, when the flood came in, this was an image which was taken and given to Google image search, and that was a classification happened. Problem is that these well-trained architectures are not trained on all sorts of variations. Rightfully so, because there are only few billion images that are there right now, right? Particularly, some of these samples may have been missed while doing data collection, or an airplane crash is classified as an airplane park on the tarmac at an airport, right? Because how many airplanes crashes we have recorded in the human history, right? So again, these are all small sample size problems in medical world, in other object recognition problem statements, and so on and so forth. Right. So with respect to the healthcare, this is one example that I wanted to highlight today is cataract. So here are some examples when we went out for data collection. There was a research problem actually told to us that what happens if someone undergoes cataract surgery, what is the impact? Originally, the problem statement was what is the impact on iris recognition, and slowly we went into understanding can we detect cataract, and then when we went on discussing with different doctors in different hospitals, including PGI Chandigarh, they highlighted that this is a major problem in Indian ecosystem. Like almost 60% of people above 60 develops cataract. And it's not that means when you develop and when it starts developing, you have to go and get the surgery done. There is a waiting period also, right? It has to mature before actually you go for a surgery. However, patients actually go to the primary and tertiary, secondary and tertiary care centers quite often to just meet the doctor and get the test done. This just increases the overall workload. Now, the question that was posed to us that can we build a cataract detection algorithm uh, using some very cost-effective sensors so that people can do it at their home. They don't need to come to the secondary or tertiary care centers, or at most they need to go to only a primary care center where this test can be done with a click of an image. And that's how our research on cataract detection started. And when we collected data, we realized that this is a big problem in terms of, first of all, there was no data set available, means the maximum was about like 50 samples available as a part of some other data set. That was completely insufficient for doing training, testing, anything, and for any analysis. The second problem we realized that when we use the existing algorithms for even as simple as size segmentation, the algorithms fail miserably because the characteristics, because of cataract in the pupil, just changes, and then the parameters that were used to fix the segmentation algorithms completely changed the moment actually people had cataract in their pupil. Even after cataract surgery, because of some of the complications, uh, again the algorithms were failing, and these are some examples shown over here in the last 2 rows. Now, it's not that cataract is going to, like, means it's a very complicated surgery. It's not like that. However, the way actually in India, because of population, more people and less doctors, the surgeries are going on. Is like in a day, let's say 100 surgeries are done in a camp. There is if even a 10% error rate for some complications in the surgery, these 10% population gets affected, and then the algorithms actually fail again for those cases. Right. So again, this becomes further like a within a small sample size problem. This becomes further complicated. So we when I was in IIIT Delhi, we collected actually we went to some hospitals in UP and did data collection, and we analyzed the results of the standard algorithms. And if you see the first part where most of the segmentation algorithms, most of the algorithms which are deep learning and non-deep learning algorithms were failing miserably. They were not even able to detect the iris and pupil boundaries to begin with, to understand what is my region of interest. The very first step in the pipeline. Whereas if you give healthy images, these algorithms are working very like in a like almost 100% accuracy. Same algorithm when we gave cataract samples, all the algorithms, actually most of the algorithms failed. And the problem was the major challenge that actually we realized in training these algorithms is uh, non-availability of data set. The data set that we prepared and released to the community had barely 2,000 samples. Before that, it was barely 100 samples. So even data collection, while cataract may seem very simple problem, right? So like this, as I said, like 60% of population, about 60 has cataract. So it's a huge population. Why don't we just go around and collect data set and build the training, build the deep learning models? However, doing even data collection for such a problem statement itself is it became a major challenge. So we could do data collection for almost 2,000 samples only. Right? So this was one of the major challenges. The data itself became a major challenge while we needed to build algorithms. Other interesting problem that we were working on was, and we have been working on, is a malnourishment problem. It's a major challenge in this part of the world, particularly in the state where right now I am in, Rajasthan, where even if actually you're feeding your kid with the right amount of food, because of lack of nutrition, many a times kid actually become malnourished, and parents, because of no information related to like what is malnourishment and what not, many times actually they skip when recognizing if the kid is malnourished. Obviously, there are cases when actually the parents are not able to afford food for their kids. Now, so our problem statement was that, can we actually, looking at the face image itself, can we actually classify a kid being healthy or malnourished? And when we started this research, again, this research started when I was in IIIT Delhi a few years ago. And the first problem itself we faced was data set. There was no data set on this problem statement. We all had been talking about malnourishment for ages, but when you really sit down to do research, you find that there is no publicly available data set to conduct this research. again, we had to start the first step of data collection itself. And there also we realize it's not easy, it's not trivial to do data collection for this kind of problems. So if I can be a little bit more bold to make a statement that for every large sample size problem, there are hundreds of small sample size problems, particularly in the Indian context. Just look around, whether healthcare or any other domain, you can find small sample size problems and with very few solutions sitting out over there, right? So or no solutions sitting out over there. So we as a developer of AI algorithms or creator of AI algorithms, we should actually strive for solving some of these small sample size problems and just not run behind the large sample size problems like solving only ImageNet problem rather than solving more ground truth or ground level problems. That's some of the problems I just spoke about. Here, at least my experience in Indian context has been that while the problem may look non-small sample size, the problem may still look like the data may be available for like in bulk. However, those are your testing data sets, not training data sets. Right? So even collecting, preparing, curating training data for building AI models is still a challenge. And the test data set is going to be humongous. Everyone wants actually to test your AI model, but rather not give any training data. Right? So in such applications, in such scenarios, how do you build deep learning models or CNN models for when we have only limited training samples? So generally, the SQ problem or small sample size problems, they are solved based on some of the techniques like data augmentation, the a priori information, taking feedback from a priori information, and so on and so forth. Right? However, in the deep learning world, in the modern deep learning world, there are several other techniques also which exist, like online learning, ensemble learning, domain adaptation, even as bold as lifelong learning, like you continuously just keep on learning the models as and when you see the training samples. Next, so there are several research threads which are going around now to solve the small sample size problems. And several researchers have been focusing on some of these threads. Now, let me actually talk about the second keyword. It is about trustworthy. So creating an AI system is not sufficient. Creating a trustworthy AI system is the need of hour. We need to actually build the AI systems where we can confidently say that if this decision has been made with 95% confidence, then I can rely on these outputs. Right? Building a trust on an AI system is paramount. Right? This is paramount interest. If as an AI researcher, suppose if you build an AI system for doing computer assisted diagnostics, now whether you are going to trust for your loved ones on this CAD system for making diagnosis or not. Right? So when let's say if I have to take my parents or my loved ones to see a doctor, I would like to do what? I would like to actually first look at the reviews of the doctor, look at the feedback from other my knowns, friends, family members, other people who would say, oh, go to this particular doctor. He's very trustworthy. He's very good. Then means after this whole research, I would go and see a doctor and say that, yes, here's my family members. Please give feedback and diagnose. Can we have such a trust on an AI system when we are saying that, okay, we are going to actually build AI system to assist doctors? And when we say building trusted AI systems, the components are like explainability. They should be fair, right? They should have a robustness in terms of different outliers. Right? They should be transparent in their decision making. If let's say an AI system says that looking at all the symptoms, I feel this is hypertension. I'm sure means if a doctor sits in front of you and doctor gives you a diagnosis, you look at all the reports and you ask the doctor, can you please tell me uh, how you have reached to this particular conclusion. And doctors will actually explain you looking at different reports, healthcare reports, and then will tell you, okay, because of these reports, this is my diagnosis. Right? If a doctor gives you that kind of information, you feel more comfortable. Right? So that comfort has to come in an AI system also, and then that trust has to be built in when we are designing the AI systems. Right? Here is one example to highlight the challenge, and this is from one of our recent submission. When we started working on skin cancer classification, we realized that there are different types of skin cancers, and the kind of uh, properties these different samples show. They're very unique, like even from the background skin color and so on and so forth. If you train on one data set, let's say the top row is one data set and bottom row is another data set. If you train on the samples pertaining to top row data set, and if you test on the bottom row data set, the kind of variations these samples are showing, the algorithms actually fail miserably. Now, if you have trained an algorithm on the data set collected in the Western world, where the skin color is mostly light, let's say, okay. Now, if you test the same system here in Indian context, in Indian scenario, the algorithms would not work. In fact, there are documented studies which have actually articulated that a model trained on Western world would not actually get translated into the current world. Another interesting example is the chest X-rays model trained on Western world when tested in Delhi for people having respiratory problems. Many of these systems were not actually behaving the way they should behave because of the pollution problems. So the kind of information changes has happened because of the pollution problems. And the Western world data may not have actually incorporated that. And on the right hand side, if you see the charts, the red curve, which is the baseline curve, highlights this. That when we do this transfer learning from one domain to another domain, still it is not actually improving the results when we have trained on one data set and test on another data set. So while the other two graphs, so the blue and green curves are our proposed algorithm, that shows that means we can do better, much better than the baseline approaches or the standard approaches. However, there's still actually a long way to go. The second example is on facial expression analysis in children. Uh, this was another interesting problem given to us by psychiatrists, that when they talk to children versus adults, they see a lot of variations in their expressions. Right? So if an adult is angry or happy, their facial expression is going to be very different compared to the facial expressions which are exhibited by children, particularly if they have some psychiatric illnesses. Right? So if you see the angry faces of children versus angry face of adult, they exhibit huge difference. Right? So now if an algorithm trained on expression analysis for adults is tested with expression analysis for children, there's a huge data shift. So again, here we observe very few samples for children. Even for those samples, when we did this analysis, like, okay, if we compute the average angry face of all the children, it looks like that the child is smiling to me on the right hand side. If you see, it looks like the child is smiling, or at least the algorithm started giving this as a smile rather than an angry face. Right? So this is another problem that one can highlight, and one can observe that even in the data shift and explainability of the models is a major challenge. Now, the next question I want to highlight, like to showcase with this particular example or with this particular question. Do you know who is this person? Anyone from the audience? As a hint, he's a famous celebrity. Famous or not famous, depending on whether you like the person or not, but he's a celebrity. No, not Sachin Tendulkar. Anyone else? Let me give you a hint. His father is a famous celebrity. And he's famous. Yes. So he's Abhishek Bachchan. Now, what problem we are talking about over here? This is a problem of kinship detection. Means generally for kinship analysis, what we do a DNA analysis, right? So to prove that a person, the two individuals are belonging to each other or not, we generally do kinship analysis. And a couple of years ago, we were doing this research on can we use facial um, features to build that connection and give not maybe as high as what DNA gives, but at least comparable level of showcasing that the kinship analysis can be done by AI systems. So at least when we started doing research, the largest data set available for conducting this research was 400 pairs. 400 like set of people only. Now we are expecting to beat a DNA based approach, DNA based kinship analysis approach with 400 pairs of images. Right now, even the largest data set has, I believe, means I'm not too sure what was the status right now in 2021, but till 2020, it was just a few 100,000 samples only. And obviously, in the last 5 years, we have seen a huge progress in the data collection on this problem statement. But still, like when we talk about large sample size problems with millions of images, here we are still talking about few 100,000 samples only. And an expectation is that we beat the DNA-based approach. Right. So these are some sample problems that would highlight the problem of small sample size and the problem of limited data or data shift. Right? So when we look at traditional deep learning algorithms, we fine tune the some layers, right? If you have some samples, very few samples, then we fine tune the FC layer and softmax. If you have a little bit more, then actually we also fine tune some of the con layers. These are our traditional approaches for doing transfer learning or domain adaptation. However, when we use the same concept for, let's say, newborn face detection, this does not actually work and then give barely like 25-30% accuracy. So we proposed an approach where we actually not only minimize the total number of trainable parameters which can be trained easily on small sample size problem, but also introduced the concept of structure and strength in the deep learning architectures. Right. So generally, what happens in the deep learning approaches is you have these trainable parameters, right? And these trainable parameters or filters are in millions. The overall weights that we actually try to optimize, they are somewhere in a couple of millions. Even the older ones had a couple of billions. Right? So even if few million parameters are there, you need a sizable amount of training data to train those millions of parameters. The task that we had in our hand, that can we reduce those millions to few 100,000 or even lesser. So we proposed in our CVPR paper the concept of structure and strength in CNN, where we highlighted that if we let's say freeze the deep learning filters pre-trained on any data set, and we based on the test this small sample size data set, we attune those filters, that would still give us a good performance compared to doing transfer learning of several parameters. This would also give us flexibility in that how much we want to change. Okay, so just to give you a big overview of approach, if you're using a conventional convolutional neural network with a small block size of 3x3 filter of 8 filters, the total number of trainable parameters for this small CNN, just a one con block, is 24 cross 3, right? So 9 cross 8, 72 values which are getting trained over here. Fine. What we did, we said, okay, let's freeze the filters. Let's obtain the filters from any data set. It can be imaginary data set, it can be any other medical data set. And then we introduce the concept of strength of those filters. How much the filter would contribute in making the decision for a new small sample size problem. So every filter is then actually associated with one strength parameter. Now suddenly these 72 parameters are reduced, and now we have to only work with or train only or obtain only 8 parameters. Right? So this is a very small example to highlight that if we can reduce the number of parameters by this number, then we have shown that we can go up to one order of magnitude in reducing the number of parameters. That would certainly help us to manage the small sample size problems. Okay, so we tested on several small sample size problem statements, but as the interest of this particular forum is on healthcare for children data set that I talked about earlier, while the traditional approaches were giving somewhere in the range of 10% to 60%, including transfer learning and other techniques, even few short learning techniques. This simple approach of giving strength to CNN architectures was able to achieve an accuracy of over 85%. In different settings and different problem statements, it was 85% and above. Okay, for more details, you can read my CVPR paper on this particular problem statement. So I have probably another 5-7 minutes. So I'll quickly talk about another problem statement on the same lines of small sample size problem, when we are combining explainability with small sample size solutions. So as I said earlier, explainability is very important factor when we are dealing with medical data or when we are dealing with people with medical history. So again, just to reiterate, if I go and see a doctor and doctors diagnose me for something, I would actually ask at least 5 questions. Why do you think this is this? Why this medication? Right? So there's a lot of whys and hows. Similarly, and those are essentially I'm trying to understand how doctor has reached to this particular decision, right, or this particular diagnosis. So this is the explainability part. A doctor needs to explain me, a good doctor needs to explain me how he has reached to the particular decision. So in a similar fashion, we would like to explore that how with limited training samples we build AI systems which are explainable, where you can see this that the decisions made by the AI system is explainable. Okay, so this is one of our recent paper, like very recent paper, which got accepted last month only for COVID analysis, a project which is funded through Rakshak project. And let me go over and highlight the problem statement and then how we have approached it. So when this COVID pandemic struck the entire world, AI researchers started looking at, okay, how to actually do detection of COVID symptoms, while there are RT-PCR tests and other tests. But one of the modalities which people also started looking at, particularly much before it struck us in India, chest X-rays. Because the limited exposure to radiography signals, chest X-rays were preferred in the Western world, while in India we started preferring CT scans a lot, but that also actually increases the future health risks compared to the X-rays. Right? So when we look at the chest X-rays of a healthy person, this is how it looks like when chest is filled with air with with no abnormality. The shape of lung and all those features or the anatomy of lung is clearly visible in a nice fashion. However, when we look at the chest X-rays of a COVID patient, you see several symptoms. Right? So in COVID-19, you see different kinds of symptoms like opacity, the patches which are shown. Right? So some patches are based on the liquid formation and so on and so forth. And these are not going to be uniform, like, okay, this is a block and this is only one place where you would see. You would see actually variations. The only one thing which is common was that both the sides of lungs were affected, compared to, let's say, a normal pneumonia, where only one of the lungs would have been affected. And so here you can see, means in the two samples that are annotated by the doctors, that both the sides of the lungs were affected by COVID symptoms. So traditionally, means we saw several papers when we are looking at the literature and we started this research. We saw several papers talking about using ResNet, ResNet V2, LXNet, MobileNet, and then they were just like pushing whatever limited samples were there. They just pushed it and said, "Oh, we got 99% accuracy." But most of the algorithms were black box. There were no such analysis that why the algorithm is giving the result actually they were obtaining. There was no explainability. There were, in fact, very few uh, uh, studies which actually highlighted that these are really making sense. In fact, very recently there's a paper in Nature which shows that majority of these studies were far from actually being used in the real world. That actually motivated us that can we do something better, and we proposed an interesting approach. We call it as like explainable architecture. So explainability inbuilt in the architecture itself, to understand if the X-ray is healthy or unhealthy patient, whether it is COVID or non-COVID disease, whether it is the region of interest is detectable or not, right? Means which is lung region, and within lung region, where is the disease region? Why actually we are making the determination if the patient is COVID or not? So incorporating these are like, if you treat these as individual tasks, right? So if you treat healthy and healthy as one task, right? Whether we if we visualize that lung detection itself is a task, right? This is what the doctors would in the brain they would do. When we spoke to doctors, this is what actually they told, that first they will actually look at only the lung regions. Within lung region, they will start actually decoding the disease regions. Using this information, they would say that whether this is healthy or not healthy X-ray. And then if it is unhealthy, then whether it is COVID disease or non-COVID disease. And within non-COVID, if suppose if says the doctor says, oh, this is not COVID, but then what else in non-COVID it can be, whether it is tuberculosis, whether it is pneumonia, or what is that non-COVID disease can they highlight, right? So they told us that, okay, these are the major tasks that they look at. We build the architecture using these tasks, and this is a multitask architecture that we actually then proposed, and we ensure that the outputs should be explainable. Means the decoder of disease architecture, disease layer would actually tell us that if you have reached to a decision of unhealthy COVID, then this is the region of interest to look at. It also means after training on samples available, and then we also collaborated with doctors for data annotation, even understanding the problem statement, data annotation, and then releasing the data set to the public, the manually annotated data set to the public. It's over 2,000 samples we got annotated by experts for training and testing. We used, I believe, 400 samples for training, and the remaining data was used for testing. And this kind of annotations were actually done by the doctors, our collaborating doctors. And then actually, when we trained and tested our algorithm, we realized that the first task of lung segmentation was happening perfectly with the proposed algorithm, while existing algorithms were also giving decent results. The proposed algorithm actually had the highest IOU. The interesting part was with the disease segmentation. Here are some samples. If you see, the first one is the ground truth. The first sample set is the ground truth given by the doctors. And the last sample in every row is the proposed algorithm. And the remaining three are the existing deep learning architectures trained in the same protocol fashion. So because we were actually doing this in a multitask fashion, we were able to actually highlight the regions more accurately. When it was unhealthy cases also, the way the doctors just in a bounding box fashion, they annotated, even there also our proposal algorithm was able to highlight the regions more accurately. We did the explainability analysis with the GradCam, And here are some of the interesting outputs. If you see the disease mass, the ground truth given by the doctors versus the GradCam analysis of the proposed algorithm, you see this, the algorithm is able to highlight and detect those regions accurately, even if it is a COVID-19 cases or even unhealthy cases. In both the cases, the algorithm was able to pick up the signals more accurately. This was another way of doing explainability analysis, which is on TSNE visualization. So the A part is TSNE with true labels. The features that we extracted and we used the true labels to do prediction. Uh, those were these are the regions where these are like COVID cases. The remaining cases were non-COVID cases. And we use our
Mayank, they just wanted to tell you that we need to finish quickly.
just more, but just 2 minutes.
All right.
Yeah. Yeah. This first figure is with the true labels. The second figure is the predictions by the by approach. And if you see, these are the blocks where originally the samples were on a COVID cases, and we were able to detect most of those cases with a very high precision. So the key takeaways in today's presentation or today's talk is the care must be taken for small sample size problems. We should not blindly use AI algorithms or deep learning algorithms without understanding the basic properties of our small sample size problems, particularly when we're sitting in the healthcare domain. And obviously, as human beings, we always want dependability in the doctors. The same has to transpire and same has to go into the mode of AI approaches where explainability and data shift, the care must be taken for this. Right. And then obviously this is going to be a cat and mouse game for newer problems, newer solutions, and overall the frameworks that we need to build in the AI community should be around responsible AI. And this is a document which I must uh, highlight that all the audience over here should read. This is a document released by Niti Aayog on responsible AI for all, uh, for every researchers, particularly working in Indian context. Right. This is something, another interesting thread probably you all should actually look at. With that, I end my talk, today's talk. So over to you, Debarka.
Thanks a lot, Mayank. So exciting, and you have explained very simply, very important points that one should remember while making an AI. Just one question, Mayank, that how small is small? I mean, what are the kind of sample sizes you are looking at when you talk about small sample size in AI?
Right. So this is very interesting. How small is small? Like we have always heard how large is large. Right. For some cases, even we have samples as low as like the entire train test sample set that we can obtain in a period of, let's say, even few years is it's 300, 400 samples only. Right. Means there is, yeah, I mean, there is a disease, at least particularly very prominent in one of the districts here in Rajasthan, is called silicosis.
Right.
Almost 2 years of data collection has fetched barely 400 samples, because you need to have those patients and you need to have the doctors who can do the data annotation for those patients. Even because that's a very special uh, uh, disease which requires that kind of understanding by the doctors themselves, whether this is pneumonia or tuberculosis or silicosis or even silicotuberculosis. Now, if we say silicotuberculosis, this means that both kinds of problems are there in the patient. This has become further narrow that can we have a AI system which is not getting confused with tuberculosis with silicosis.
Got it. No,
So samples can be very small.
right. Thanks to running all these companies that I also have faced many such problems of small sample sizes in biomedical molecular diagnostics
Yeah.
as well. The amount of data that you typically acquire, even after spending, tens of lakhs of Indian currency, it's very small. I think but tell me something. Is it like, so you are talking about image data primarily, right? But what about tabular data, matrix, right? Where you have not only small number of samples, but oftentimes you have small number of features as well. I mean, so
Yes.
do you see a difference between the tabular data, matrix data, and visual data?
Yeah, see, means there, in fact, the problem is much more complex there because, see, here with image data, you see, end of the day, these are all data points in the feature space, right? Whether it's tabular data or image data. How many
Right.
sample points that you have in your feature space to even train the model? Uh, means if you have just barely like 10 samples, 20 samples, that is going to be more challenging. In fact, the kind of problems you are mentioning,
Yeah,
uh, applying the deep learning architectures are going to be very challenging. Means
exactly.
not going to be straightforward.
Yeah, exactly. My ideas are similar on that. So I think if there's any other question from the students, I don't see any question on the question and answer thing, but I'm so surprised that you guys don't have any question because it's such an exciting and you know talk and nice features of AI. So one should always ensure every time using it in their respective sciences. But anyway, if you are right now not ready with your question, you are free to write to